A small set of polystyrene balls floating in the air may not seem at first glance a finding destined to occupy scientific headlines. However, this seemingly simple system has allowed us to observe a phenomenon that until recently belonged almost entirely to the theoretical field, a classic crystal of time that remains active without the need for an external periodic impulse. If you like the content, do not forget to subscribe and give like, so you can be aware of more fascinating discoveries in the world of science. The experiment, developed by a team from the University of New York, shows that these structures not only exist, but can also be seen at the naked eye and manipulated with a portable device. The work, published in Physical Review Letters, describes how two sound levitate particles can enter a stable oscillation state that breaks the system's temporal symmetry. A conventional crystal is defined by its ordered spatial structure, while a time crystal is characterized by a periodicity in time. This means that the movement is repeated regularly, even without a constant external thrust, generating stable oscillations as emergent property. This idea implies that the system itself chooses a rhythm. It does not simply respond to an external force, but maintains a stable boundary cycle despite friction and energy losses. The relevance of this concept goes beyond theoretical physics. Time crystals allow you to explore complex collective behaviors in seemingly simple systems. They also help to better understand the boundary between passive and active systems, a key distinction in fields ranging from soft matter to biology. The experiment is based on an acoustic levitator that generates a stationary wave of sound in the air. This wave creates pressure nodes that act as energy wells, trapping small objects against gravity. In this case, spheres of expanded polystyrene. Each sphere is contained in one of these nodes, as if it were held by an invisible spring. The force responsible for this confinement is known as Gor'kov's force, resulting in a surprisingly stable system where particles can remain suspended for long periods of time. What is really important is that particles interact with each other through the sound waves that disperse. This wave-mediated interaction is the motor of the observed phenomenon, allowing the forces between them to be non-reciprocal. When the spheres have different sizes, this asymmetry becomes crucial. The larger sphere scatters more sound, and therefore affects more intensely the smaller one. This allows to extract energy from the acoustic field and transform it into sustained motion. The spheres of polystyrene, by interacting in a non-reciprocal way, acquire typical properties of active matter. Active behavior arises from the relationship between elements, not from isolated elements, which is fundamental to understanding their dynamics. Under certain conditions, non-reciprocal interaction compensates for friction losses, leading the system to a sustained oscillation regime without the need for an external periodic impulse. This allows access to dynamic states that meet the definition of crystal of time,